So, good evening, everyone. So, welcome back to 1258. So, this is the agenda for today. Okay, so, we'll continue what we discussed last meeting, production to completion plan system technique. Then, discuss about measurement scale, and then the main part of this is the linear programming. So, uh, yeah. From last meeting, is there any question or review? Uh, right. So, okay. So, in your group projects, okay, you're supposed to use all these uh, analysis tools and method that we discussed in our class. Yeah? So that's including programming, prioritization, modeling, uncertainty and risk, game theory, or dynamics, and group decision, doing theory, and financial and economic analysis. Okay, and last meeting we discussed the dependency among these uh, analysis tools. Okay, then as a recap, we also discuss why do we need this type of analysis, and then we go to the framework, yeah, that you start with assuming of data collection by demand and supply side. The supply side usually the network, and then the demand side usually the flow, yeah, in transportation. And then you analyze both current pattern and the future pattern. Okay? And then you compare the two sides, yeah, demand side, supply side, current pattern and future pattern, okay, whether it is adequate or not. Then you propose an alternative solution, and you analyze feasibility based on financial feasibility and economic feasibility, and then you prioritize them. Yeah. Once you have the priority projects, then you strategize how to implement that better. Yeah. Eventually, the one of the most important but often forget is the feedback. Yeah, to come back to this to make the whole framework as a feedback loop. Okay. Now we discussed also several insight of analysis. Okay, last meeting. Okay, and several factor including the demand and supply. All right. I think the last one is I want to remind that we have what is called financial feasibility and economic feasibility. Okay. Financial feasibility involve the actual cost and revenue associated with the project. Okay. While economic feasibility include more indirect, yeah, impact of the project. Yeah. Both direct and indirect. The direct cost and benefit represented by the financial, but indirect and intangible effect that would include the economic, yeah, environment, uh, social equity, including politics, yeah, and military. Yeah, that's include national unity and so on. Okay, so then we don't forget that we want to create a safe transportation. Okay, so this is our last part. Yeah? So now one important uh, relation between transportation, yeah, and land use. Yeah. This is very important to promote, yeah, compact and mixed land use development. This is our goal, yeah, and reduce reliance on private vehicles. So this is the feedback loop uh, framework, what is called land use transportation interaction. So we can start anywhere. This is a loop. Okay, say we start with from the top here. So say you change the land use. Okay, say from farmland you make it into a factory, or from uh, farmland you make it into residential area, and so on. So because you change the land use, automatically it changes the activities in that area. Okay, so change in land use pattern will eventually, yeah, in the short-term effect, this one is the red part here is the short-term effect. It will create a change in the demand of transportation. Okay, so now the change of the demand in the transportation eventually, in the long term, uh, because there is some greater need for new transportation, then you will change the transport facilities. Yeah, that's include the road width, the road network, the station, terminals, and so on. Yeah, that eventually will change also the traffic volume, yeah, per direction. And this change in the transport facility will eventually change the accessibility, yeah, to that piece of land. And because accessibility to the land change, then the land price change. Okay, that change in the land price will trigger the change of the land use. Hmm? So then we have this feedback loop. Do you understand? Any question about this? Yeah, this part, change in the land use and change in the transport facilities, and representing the change in the infrastructure. Okay? But when you change the activities, yeah, these are the activity change. So remember this, transportation is derived demand from activities, and activities is derived from change of land use. Okay, so the change of land use comes from the change of the price of the land price. Okay, and the land price change because of the accessibility. So these are the uh, model that you can actually create, yeah, based on this feedback loop. Yes,
Hello, sir.
yes. So,
I'd like to ask that this is the common framework for
mhm.
transportation planning. So, uh, it assumes that the transportation is the means to the ends. Yes, is that
No,
correct?
no, no.
Or
Uh, uh, the transportation is, because this is a feedback loop, it's a loop, right? So this
okay.
is not the end, of course.
I mean, sir, are the activities the ends and the transportation is just an effect because of the activities?
Correct.
So, my question there is how do we account alternative causes of travel like leisure traveling or probabilistic?
Yeah,
uh,
that part will be in here in this yellow part. Yeah,
okay, but what if the transport demand was derived other than not because of the activity? or the land use in the area, but because it's just accessible, or or people just like to travel randomly.
Okay, so that's also correct. Okay, what happen if people just want to leisure, right?
Yes, sir.
So that also actually include in this model, because there is some activities of tourism, yeah, that you can also put here as an activities. Okay? Then the transport demand is based on that activities that you have. Take example the city of Barcelona. Yeah. So almost the whole city is dedicated for tourism. So then they create planning, okay, with a very excellent bus system only for tourism, for example, okay, to visit all the tourist spots. So this is part of whether they are using for leisure or using for the real active economic activities that the normal way, for example, trading industry and so on, we can still use the same model. Okay, so there is there are many model based on this pattern. You can check in Google, for example, Lowry model uh, is very common for land use transportation interaction. uh, Aside from that land use and development, okay, we also want to improve, yeah, efficiency in terms of transportation service. These are the factors that we usually use. Okay. And there are many methods, okay, and analysis that we can use for improving the efficiency with myself as well. So for example, in a region that you want to have multiple transit agency, then you want to set the fare, you want to set the schedule, okay, to maximize the ridership. In this case, many uh, methods that we discuss in this class, including game theory, decision theory, the flow, and linear programming, can use. Okay, so the same thing if you have two neighboring cities. For example, you want to decide whether to invest in a shared airport, for example. So one city prefer the other to pay the investment, but both will benefit from the airport. So in this case, you need negotiation, right? So negotiation itself is a part of game theory and decision theory. Yeah. And ideal for network of power dynamics, we can also use that. So, okay, this is an example that you can have situation or insight that potentially come from beyond the traditional uh, transport demand modeling. This is what I want from you. Okay, you probably have learned. Okay, many of you are or you have learned four-step model, transportation demand modeling. So in this class, I want you to innovate better than that. Okay, that's why we explore other methods, yeah? Other type of analysis than the usual four-step models. Is that okay? So similarly, when you have a transport project, okay, you will have many stakeholders. Yeah, stakeholder engagement are vitals in transport planning. Again, uh, if you said you have stakeholders, that means group decision making, isn't it? Okay, so how do we reach consensus? Okay? The part that we will discuss in our class in this semester, yeah, derived method, group decision making, okay, game theory, power dynamic of IFNs, this can be used, okay, for stakeholder engagement. Okay, so I hope you understand the big picture here. Now, okay, I want to give you a very simple numerical example. Okay, this numerical example comes from the book of Mannheim. So I also included chapter 1 of that book in Moodle. So you can also read in more detail. Okay, so imagine you have a highway between two towns. Okay, so these are the variables that we will discuss. Yeah. So we have demand and supply. So S represent the demand, supply. D represent the demand. T represent the system transportation, and A represent the activities. Yeah. So the land use is already included in this activity system. Okay. So that represent by the population, social activities, and so on. Okay. And the system transportation be simplified into two ways, two-lane road, yeah, for 10 kilometers. So the demand represented by the volume, yeah, of vehicles, so per hour, and the supply represented by the travel time, yeah, in minutes. This represented level of service. Okay, so I want to give very simple model. Both are linear. Okay, so here we have the supply. Okay, the first model, the supply S is a function of transportation and demand. Okay, in the second model, you have demand is a function of activities and the supply. Yeah, and we use both of them are a linear model. So this is the actual model, linear. Okay, this is the first one, and this is the second one. Okay, so now the transport system, okay, represented by these two parameters. Yeah, M represent a free flow travel time, so say 10 minutes initially, and then N here represent the congestion effect. Yeah, say 0.01 minute per vehicle per hour. Okay, so this is the first model. Okay, and in the second model we have demand model, which is demand function of activities and supply. Okay, so the activity here represented by these two parameters, yeah, A and B. Yeah, what is A? A represents potential demand. Okay, whether you have travel time or not. Okay? Say T is zero, for example. T is here is travel time, right? So if T is zero, A is still there. So there is 5,000 vehicle per hour potential demand. Okay, but when the travel time is getting larger, so then the change or the slope, yeah, the change of demand per unit time can become a B, which is minus 100. And why minus? Because the demand, the volume in here will go down by the travel time, yeah, from the potential demand. Are you okay with this? You have two linear model, yeah. So so let's put them together in one. Yeah, so this is the supply and this is the demand. Okay, so if you put them together, what you will get? Okay, so you will get this point. And so you have two equations and two variables, right? So you can use elimination to get the V and T. So you get 2000 and T is 30 minutes. So you get 2000 volume and 30 minutes. So this is our initial condition. So let's call this scenario A. Yeah, the base scenario. Okay. So based on the demand and supply, you will know the volume and the travel time. Okay. Now let's do what if analysis. Okay. So the first what if analysis, this is scenario B. Okay. Say you have a new highway. Okay. It's built as an alternative link. Okay. Because you have a new highway, what changed? Yeah? The congestion effect is reduced. Yeah? Earlier was 0.01, now become 0.05. Sorry, 0.00. Yeah. So this model is still the same. Yeah. Only this part changes, right? Supply change. Yeah. The demand model does not change. So in that case, we have new equilibrium. Okay. The volume from 2000 now increased to 26, while the travel time 30 minutes reduced to 23 minutes. Improve or not? Yeah. So the existence of new highway, yeah, improve, yeah, improve the travel time, right, from 30 minutes to 23 minutes. So reduce the congestion, yeah, and then also increase the volume. What does it mean? Yeah. So if you have a higher volume, that means higher activities. Right. So economic is better. Okay. So this is our first point. Yeah. Now become change down here. Yeah. Become F2. Okay. Now what happen if we have scenario C here? Yeah. So in scenario C, suppose and after some time, so the population and economic increase. Okay. So in that case, yeah, because population and economic increase, so in that because population increase, so the potential demands also increase. Yeah, from 5,000 a while ago now becomes 7,500. Okay, because economic increase, so there is a value of time also increase. Okay, so B from 100 minus 100 now become minus 150. Yeah, so become more sensitive. Okay, so what happened? Hmm. The volume increase. Yeah, here volume increase to 3,430, and then the congestion also increase. Yeah, from 23 now become 27. Yeah, from 2,600 now become 3,400. What does it mean? Okay, the volume increase, that means the activities is indeed, yeah, improve. Okay, but congestion also increase, yeah, a lot. Yeah, from 23 now become 27. Is that okay? Yes, George.
Sir, when the demand exceeds the supply, should planners... sorry, sir. Okay, sir.
One,
About this, about the question on of supply and demand. So when the demand, sir, exceeds the supply, should planner focus more on increasing the supply Or the planner also should manage the demand. So how this analysis help the planners decide?
No, this analysis is not about demand is over supply or supply below demand. This is equilibrium. That means exactly the same. Demand is exactly the same as the supply in this analysis. So, but to answer your question, so when you have the demand is over the supply, right? So
Yes.
then there are two options that you have, isn't it? Either you reduce the demand or increase the supply.
Because in your second diagram, sir, you add an additional highway so that we can reduce the travel time from
No, no.
30 to
Again,
23.
we have different mindset here. What you have in your mind is the demand over the supply. Okay, this is not what happened here. Okay, what happened here is equilibrium. Okay, equilibrium means exact the same. Demand is exactly the same as the supply. This is the point of equilibrium. Can you understand the point of this? Okay, uh, demand over the supply is in this area, isn't it? In this area, supply is over the demand. So in this area, okay, let me throw in the different color. So in this red area, yeah, so demand is higher than the supply at this point. And then if I throw in this green, yeah, so this one, the supply is higher than the demand. Okay, we are not interested in that. So in this model, we are talking about equilibrium. Okay, at equilibrium, that is equal. Demand is exactly the same as the supply. Do I answer your question or okay? So, but if you're asking what happened if demand is over the supply or the supply over the demand, then you have two options. Yeah. Either you cook the demand to the supply or you cook the supply to the demand. So, but in this example, in this particular example, we are not talking about the larger or inequality. We're not talking about inequality. We are talking about equality. Okay. So in this example scenario A, you have equality base scenario. First, you have 2030 minutes. This is our initial. Okay. And then in the second scenario B, again, these are also equilibrium. Okay. Without changing the demand, can you see the demand is exactly the same, 5,000 and then 100, right? So the demand does not change, okay? But we already increased the new highway. So we already improved uh, the road network. Is that okay? So in the scenario C, okay, uh, we assume here this is exactly the same as this, 10 and minus 0.005. That means the supply, okay, does not change, but the demand change. Now become 7.5, and instead of 5,000, we increase to 7.5, and then this is become 150 minus 150. Is that okay? So can you see the story? We start from F1, okay, initially, and then improve the road first, going here, right? And then the activity change, now going to F3. Yes, but Paul.
I think can you hear me, sir?
Hmm.
Okay. I think these three scenarios perfectly described what we call induced demand in transport planning. Because when we introduced a new highway, basically building more roads will only encourage more people to buy more cars. And on the first two scenarios, I am aware that our base data was only 2,000, but now that there is a new highway available for them, therefore it encouraged more travel, it encouraged more economic activity. Hence,
Hmm.
the demand suddenly increased from 2,000 now to 7,500. Then
Okay.
the travel time also increased again to 27 minutes. So I
Okay.
think
Good.
it just it
Yeah,
could be a
the,
perfect
the normal
representation.
scenario, yeah, the effect, yeah.
Yes,
So
so it
now
would
what
be
happened, Paul? What will happen if initially we did not increase the highway, but the demand is actually increased?
it could be a lot worse. It would be a lot worse because the travel time would increase significantly.
Correct. So that's exactly what scenario D is here. So this is the scenario D.
Oh, okay.
Okay. So what happened if the population and economic increase, but there was no additional highway? So it's still the same, yeah,
Mhm.
the old transport system, but the activity changed. Yeah. So because of this, you will see, yeah, the congestion is beyond 30, yeah, beyond the initial, and the volume is actually increased little from 2000, okay, but it's much worse. Yeah, so this is the summary. Yeah. So can you see which spot you are going is up to you as an urban planner or transport planner. Yeah, whether you start from uh, F1 to F2 and then F3, yeah, or you come from F1, F4, and then F3. Okay? So, but this is a simple example using very simple linear model, okay, to show the interaction, okay, between transportation system and activities. Yeah? So land use uh, transport system. Is this clear or not? Yeah. Is there any other question about this? Oh, there is a chat here. Okay. Okay, so with that, I guess this slide is done. That's supposed to be last week. Okay. So now, is there any question about that first part of our discussion? If not, I want to give you the foundation, yeah, about data. Okay, so this is a part of the. Can you see my slide? No?
No, sir.
Oh, okay. Now can you see? Okay,
Yes, we can see.
good, good. Okay, so you can follow this slide in Moodle. Okay, so what I want to discuss here, probably you already know. Okay, but I want to emphasize certain things before, because the whole semester based on this one. So I need to give you the foundation. Yeah. Okay, so data can be classified. Yeah. So we are looking for two ways to classify data. Yeah. Is it a label or is it number? Okay. So that is a qualitative versus quantitative. Okay. So second, how much mathematics we can do with it. Yeah. That is a level of measurement. Yeah. Measurement scale. So we cannot simply trust the number, yeah, just because it is a digit. Yeah. So sometimes number is just a label. Okay. So the measurement scale represents the amount of information contained in the data. So let's define qualitative, which describe the quality or category. This one have two possibility. One is called nominal, the other one ordinal. Okay? And quantitative describe the quantity, the amount. So this can be based on distance, interval, or based on the true absolute zero. We call it ratio. So qualitative data, okay, is the data that can be placed into distinct categories. Okay? So sometimes we can arrange into meaningful order. Yeah? Sometimes not, right? For example, blood type. Yeah. A, B, or zero. Yeah, O sometimes. Yeah. And then if you get assignment, yeah, maybe fail, pass, good, excellent. So the first part here, the blood type of a person, yeah, is there any order? No order,
Yes, sir.
right? Yes. So how about the assignment? Fail, pass, good, excellent. Is there any order? Yes. Right. So you would say, yes, pass is better than fail. Yeah. Good is better than pass, right? So there are distinct category. Okay. Sometimes have order, sometimes not. So these are called qualitative data. Okay. While quantitative data, okay, are numeric in nature. So yes, they can be run in order. Okay, they can admit arithmetic operation, and this quantitative data now can be classified into two, yeah, format. One is discrete format or continuous format. Yeah. For qualitative, is always discrete. Okay, so the data format, discrete mean countable. Yeah, there is no intermediate value exists. While continuous, that means measurable value. Yeah, so that means real number. Okay, there is infinite possibilities within the certain range. Yeah. So the data format you need to distinguish from the measurement of scale. Okay, so don't confuse with the four scale. Yeah. So, discrete data jump from 1 to 2, right? While continuous data flow from 1.1, 1.11, 1.111, and so on. Okay. So usually ratio and interval data are continuous. Okay. While the count, okay, it is ratio, are discrete. Okay. Now, discrete data assume can be counted. These are examples. Yeah. Zip code, the count, frequency, yeah, the set of digital count, number of words in the collection of document, number of children in the family, number of cars, number of house. Yeah. So discrete data analog to the steps in the staircase. Yeah, is countable. So you can have integer or binary. While continuous data assume all the values are within the line, number line. Okay, so usually we use real number. In reality, when we set real number in computer, usually we use floating point. Okay, in reality, the computer does not actually have a real number. This is technically discrete, but we just approximate the continuity. So you don't feel it. Anyway, so real value can only be measured and represented using finite number of digits. Okay, so example of this continuous data, including temperature, time, height, and weight, and so on. Okay, so this is the kind of summary. So data type consists of qualitative and quantitative. So in the measurement scale, qualitative can be nominal or ordinal. The format is discrete. Okay? While the quantitative in the measurement scale can be interval or ratio, and then the data format can be discrete or continuous. Up to here, any question? Is it clear? Good. Okay. Now, let's go deeper to the four measurement of scale. Okay. So nominal, ordinal, interval, and ratio. Okay. So this is the order. So nominal is the lowest. Yeah. Higher than that is ordinal. Higher than that is interval. The highest data type, in terms of measurement of scale, is the ratio type. Okay. So qualitative data can be either nominal or ordinal, right? So this is an example of nominal. So gender, a nominal. So you can represent male as 1, female as 2, or you can represent female as 1, male as 2, and so on. So the number just represent the label. Okay. So there is no order in nominal data. They are just label category, only distinct category. Okay. And then when there is an order, we call this ordinal. Okay. So for example, the sequence, the order of choice, and so on. Okay. Now, by definition, nominal data, okay, or we call it label scale, classify data into distinct, mutually exclusive categories, so non-overlapping, okay, and no order exists. The key properties is distinctness. Okay, there is no order, just count. So you can only get the mode. There is no mean, no arithmetic mean, and there is no possibility to do sorting. When your data is nominal data, which is just label, so there is only distinctness, equal or not equal. So these are examples. So the fruit I like is apple, banana, orange. So it's up to you to define apple is what number. But if you put, say, apple is 1, banana is 2, it doesn't mean that 1 is less than 2, right? Because this represents distinctness, not order. Other example are blood type. So student ID number, eye color, zip code. They look like numbers, but actually they are text. Okay, including hex color of the web. Okay, they look like number, but they are actually labeled. Is that clear? Okay. The number or only symbol, there is no meaningful value unless you assign to the label. Okay, so say gender is a nominal value, so you can assign one male, two female, but you can change uh, whatever number, not just one and two. You can put 5 female, 225 male, and so on. Both representation are valid as long as consistent with your own definition. Okay. The second measurement scale is ordinal data. So in this case, you have the order scale. Yeah. By definition, it is categories that have meaningful sequence or rank. So the key property here is order. Yeah, so A is less than B. Okay. Ordinal data do not have information about distance between the rank. Okay, so we don't know the difference between the rank. So therefore, we cannot compute arithmetic. You cannot add, you cannot take difference. You cannot take minus. You can multiply, you cannot divide. So ordinal data. Okay. These are examples. Say you put comparison index. So yeah, from -2 is strongly disagree, -1 is disagree, 0 indifferent, 1 agree, 2 strongly agree. So these are usually ordinal Likert scale, isn't it? So ranking, yeah, the taste of potato chips from 1 to 10, yeah, your grade, yeah, the height in tall, medium, short, and so on. So again, priority, yeah, the rank of priority or competition rank, yeah, first, second, third. All of these are example of ordinal variables. Can you see, for example, in the first, second, and third, the difference between first and second are not necessarily the same between the second and the third, right? So there is no real distance, okay, that you can take from ordinal variables, yeah. Well, there is a way to measure distance from nominal, ordinal, interval, and ratio later if you want to discuss, yeah. So the second part is the quantitative data with this interval and ratio. In the interval measurement scale, you can have plus and minus. Yeah, so you can add, you can take the difference. In the ratio measurement scale, you have absolute zero and you can divide. Yeah, you can multiply. So what is interval data? By definition, yeah, this is a distance scale. So it's a quantitative data. Yeah, quantitative can be discrete and continuous. Yeah, so where the distance between values is consistent and meaningful. Yeah, remember, the distance is consistent and meaningful. Yeah. So the key properties here, you can do addition, you can do subtraction, but you cannot have true zero. So the 0 point exists, but this is invented or arbitrary, just based on agreement. Yeah. So example, Fahrenheit or Celsius temperature, yeah, may have 0 degree Fahrenheit, or 0 degree Celsius, but this does not represent zero heat, right? So that means you can take the difference. Yeah, so 74 degree is 2 degree higher than 72, but you cannot take the ratio. You cannot say 40 degrees is twice as hot as 20 degrees. Okay? Because interval data is not, okay, it's just about distance. It's not about the absolute zero, so you cannot divide. Another example is the date, yeah, and then basically measure of time, yeah, calendars. So the year 0, when Jesus was born, is not the beginning of time, right? So there's before Christ, yeah, BC, or before Common Era. Okay. Last but not least is the ratio data. So this is the absolute scale. Yeah, this is the best, the highest measurement of scale. What's the definition? Is a quantitative data that have consistent distance and it has up true absolute zero. Yeah, which true absolute zero mean none or nil. Okay, so usually ratio data have unit of measurement. Usually, so in this case, you can multiply, you can divide. Okay, why we discuss about all of this? Yeah, because based on the data type or measurable scale, your analysis change. Okay, so these are example of ratio type. Yeah, the height, the weight, age, yeah, money, yeah, temperature in Kelvin is also ratio type. Yeah, the count or the frequency is also ratio type. Yeah, implication, you can say 20 meters is exactly twice as long as 10 meters. Okay. Now, this bar represent the actual length in ratio. Okay. Say, for example, 5, 7 milli, 8 milli, and so on. Yeah. But when you put them into ordinal scale, now become 1, 2, 3, 4, 5. So I give you another example. Money. So you're asking in your questionnaire to your respondent about the income. Okay. How much is your income per year or per month? Right? So it varies. Okay. But when you put your income in ratio type, okay, you will get the actual value. But when you ask in their questionnaire already, you put into ordinal measurement or interval, then you lost information. So that loss of information you cannot recover. Okay. So this is why this is important. Yeah, the power of measurement of scale. So nominal level is the lowest measurement of scale, right? So it is the least powerful, that it provides the least information about the data. Yeah? The same income, if you ask in ratio, yeah, you will get, for example, in US dollar or in pesos, right? So, but if you put in the interval, so you will get only range, yeah, between 0 to 5,000 or 0 to 10,000 pesos, 10,000 to 20,000 pesos, yeah. So 20,000 to 30,000. So these are interval, right? You can also put it into ordinal, yeah. Oh, low income, medium income, high income. So these are order. Okay. Or you can put it into nominal. You have income or you don't have income. Binary. Right. So the same variable of income, okay, you put into a different measurement of scale. But when you put it into nominal, you have the least information. In that case, because you ask that, you cannot recover back. For example, you ask, you have income or not? The answer, yes, I have income. You don't ask how much, so you don't know how much is that income, correct? Or you ask, okay, certain range, but you don't really know how much the actual one. So in that case, okay, when you ask the highest possible measurement of scale, okay, in ratio type. So in terms of time, in terms of income, in terms of distance, and so on. So you measure in the ratio scale rather than in the ordinal, interval, or nominal. Of course, there are certain things like gender, which is basically nominal, so you cannot pass into ratio. That's clear, right? So, but when you have any data, yeah, so ratio type is the highest. Yeah. So any data conversion from higher level to the lower level, you will lose information. Yeah. So from ratio type, you can transform into uh, interval, ordinal, and nominal easily, but you cannot transform from lower to higher level. Yeah. There are certain exceptions later we discuss. Yeah. For example, in HP, in the IFN, and so on. But at this point, this is it. Clear? Okay, so now these are the type of uh, properties or attribute. Yeah. So distinctness, yeah, or equal or unequal. Order, that means larger or smaller. Addition, that means can be plus and minus, yeah, subtraction or addition. Multiplication here represent multiply or division. So nominal attribute only have distinctness. Yeah. Ordinal attribute have distinctness and order, right? So interval attribute, you have distinctness, order, and addition. Okay. While the ratio attribute have all these four properties. Okay. Now, because of that, yeah, these are the description and examples. Okay. So because of that, the operation that you can use is different. Yeah. In nominal data, you don't discuss about mean, the average. No, you only can take mode. You can even take median. Okay, central tendency, right? So, but if you have ordinal data, you talk about median. Yeah? Yes, in nominal data, you can compute entropy, there is a contingency table, chi-square test, and so on. Okay? But in ordinal data, you can have more than the nominal. Yeah, so you can have median, percentile, rank, yeah, correlation, and so on. Yeah, this is non-parametric statistic. Yeah, but in quantitative data type, yeah, interval and ratio, you will have much more operation. Okay, so you have arithmetic mean. Yeah, in ratio type, you can have even geometric mean, harmonic mean, and so on. Okay, so yeah, this is the summary so that you can see. Yeah, so nominal data type only have distinctness. Yeah, ordinal have both. Yeah, distinctness and order. So interval until the distance, while the ratio you will have all these four attributes. Yeah, and these are the best central tendencies. Yeah, mode, median, and mean. Yeah. In ratio type, you can have geometric mean. Yeah, which you cannot do in interval. Okay, practice. So what do you think? If you want to analyze satisfaction survey, scale 1 to 5 star, is this interval or ordinal? Yes, George?
Ordinal, sir.
Yes, supposed to be ordinal, right? But in data science, yeah, strictly speaking, it is ordinal. Yeah. So why? Because there is, the difference between 4 and 5 star. Yeah, we don't know whether it is the same as between 1 and 2 stars, right? So it's ordinal. But in data science, yeah, in practice, we treat this as interval. Yeah. Sometimes we calculate the average rating, but And this is very common in industry, right? So be careful, yeah. When you do this, okay, we know this is a theoretical risk. Yeah. So it's a wrong way to compute. Yeah. Why? Because you assume they have the same distance, which it is not, right? Okay, so this is the summary again. Yeah. So you have a qualitative data type or quantitative. Yeah. In qualitative, you have nominal or ordinal. Okay. In quantitative, you have interval and ratio. Yeah. In qualitative, this nominal can be binary, yeah, or many nominal. Okay. And qualitative data is always discrete, while in quantitative, you can have discrete or continuous. Okay, clear? So this is just the basic. I hope this is very clear. But if you have any question, you can ask. So in brief, I want to introduce you to, okay, so can you go to Refoleto? Refoleto distance tutorial. Okay, so here it is. So let's go to the content. So yeah, this is very long time ago. I make this tutorial. Probably you were not born yet at that time, some of you. Okay, this represent the similarity measurement. Yeah, so I'm talking about what is distance. Yeah, what is the relationship between similarity and dissimilarity? Okay, and what happen if you have measurement of scale of binary variables, nominal or category variable, okay, ordinal variables, text, and quantitative variables. Yeah, so all of these have different type of distance, including the calculator here. So this one, this is the formula, and these are examples, so you can get the computation, yeah, of the distance. So at the end, what happens if you have two groups of distance between two groups? Yeah? So you can use Mahalanobis distance and so on. Okay, and what happens if you normalize these distances? Yeah? And if you aggregate the mixed distance, yeah, so you can aggregate all of this. Let's take example. So I have these are data from questionnaire. So I have several variables here, and these are the data. Okay. So what you will do is you transform this data into coordinate. Yeah. So if they are nominal or ordinal, so you put them into different coordinate. Yeah. So once you have the coordinate, then you will have this new data type. Yeah, based on the data type you have. For example, this is mode, right? Uh, Mode is 1, 2, something. So mode is nominal. In this case, I have walking, car, cycling, and bus. So in that case, I use dummy variables 1 and 2. So I will have coordinate of 0 and 0, 0 and 1, 1 and 0, like that. And this represent the uh, walk, car, cycling, and bus. Okay. And then if you have variables of activities, okay, these activities are 6 choices between sport, picnic, reading, walking, meditation, and jogging. So they can be selected more than once. Yeah. they are nominal data, but they can be selected more than once. In that case, you will have 6 numbers here as coordinate. Okay. And for the category, for the ordinal data satisfaction, okay, so the value is between -2 to +2. So in that case, you want to change into normalized rank. Okay? So the normalized means the values between 0 to 1. Okay. So in that case, you will have this one. Satisfaction is between 0 to 1. The binary is still okay. Time is quantitative ratio type, so we don't change at all. After that, you can compute the distance. Yeah. So you can compute the distance. So depending on the data type. Yeah. Yeah. These are the examples, so you can read by yourself. Okay. And based on that distance, then you can measure many different analysis. Yeah, for example, you want to do decision tree, uh, clusterings, and so on. Is this clear or not? Any question? So I give you example, yeah, so that you will understand. Say this one. Wait. I will have the example. Okay. Say, I want to measure distance between apple and banana. How do you measure distance between apple and banana? The way to do is to gather the data about the properties or characteristic, yeah, between these two fruits, isn't it? Yeah. So you make binary. Yeah. Is the shape sphere? Yeah, yes or no? Is the taste sweet, sour, crunchy? So yes or no? Yeah. Yes mean 1. Yeah. No means 0. So you create coordinate. Okay. So based on that coordinate, then you can compute the distance. So say you have this coordinate. So yeah, apple is yes. Yeah, yes. So 4. Yeah, and then so between coordinate of 1 1 1 1 and then coordinate of 0 1 0 0 is 0.75. Another example so that you can grasp the idea. This is the common distance that you use, right? This is called Euclidean distance. Okay. Usually, what you have is, what do you usually have? Oh, a triangle, right? A triangle, something like this. So if I have triangle, so if this is 3, this is 4, what is this distance? 5, you said, yes. How do you get 5? You said 3 square plus 4 square, okay, and then you take the square root. Is that correct? Yes, that is exactly Euclidean distance. Okay? Okay. Yeah, Pythagorean theorem. Okay. But you're talking about 2 dimension here, right? Yeah, this triangle is 2-dimension. How about if you have more than 2-dimension? Dimension mean, yeah, this is, for example, weight. This represent time. This represent cost. Yeah, this represent something else. Whatever attribute you can think of. Yeah, that represent the coordinate. Yeah, dimension means the variable that you put in. So each object will have many dimensions. As long as they are the same dimension, the number of dimensions is the same, then you can calculate the distance. Is this clear or not? So, okay, let's do it this way so that you will see. The one that you just see a while ago, okay, is actually 2-dimension, right? So that one is what? 4, 0. Ah, so if you have 0, 3 and 4, 0, the distance is 5. Right. Yeah, the distance is 5. But if you have more than 2 dimension, so then you take the difference between each dimension and then you square them and then you sum and then you take the square root. Okay, that is Euclidean distance. Yes, George.
Sir, just for clarification, sir, do we need to be familiar with these formulas or this calculation for our class projects or assignments in the class, or this is only a additional information, sir?
Additional information, but
Okay.
this is very useful information. Why? Because everything that you measure based on distance. You can measure everything. If you understand this concept, then you can measure everything. You ask, really everything? Can I measure love? Yes, you can measure love based on distance. How? Then you set the attribute of love as coordinate, and then you put it as numbers, ordinal number. Then you can measure the distance. Can I measure faith? Yes, you can measure faith. How? Again, you put the features of the faith. Yeah. Oh, how many times I read the Bible today? How many times I go to the church, for example, every week? Those are measured. Okay. Probably not perfect, but these are measured. So once you understand the meaning of distance as a measurement of attribute, then you can use for any purpose, isn't it? Is it clear? Yes, yes, Andrew.
Sir, what do these objects represent and what do the coordinates represent? So,
Okay.
is it correct
Object
that the
represent
coordinates
any
are
object that you want to
okay?
measure. Coordinate represent the attribute that you want, the variable that you want. Okay, take any example that you want to investigate in transport, in your field, architect.
Sir, I'd like to refer back to the triangle a while ago. So,
Okay,
o- so the two objects there is the dimension, the width and the height. Is that correct? The width is 3.
this one?
No, how did we
Okay,
encode that as two
I think
objects, the triangle?
I have the numerical example here. So for example, this is cost, time, weight, and incentive. Yeah, so I want to measure two objects between A and B. Okay, if I know the cost, if I know the time, if I know the weight, and I know the incentive. So these are 4 dimensions. Then you compute, okay? So between 0 and 7, so 0 minus 7 square, uh, the same variable within time, so 3 and 6, so you minus. and then square, and so on.
So is the Euclidean distance a summary between those objects? Is that
No, it's the distance between the two objects.
distance between two objects?
Good.
So it's the
Okay,
difference
so
between the
maybe you get confused what is the meaning of distance.
and the objects, sir.
The object is between you and me. So I give you example so that you understand. When I go to your house, okay, uh, there is a what is called psychological distance. Okay, so when I go to your house, okay, will you use special clothes to fetch me? Probably not. Okay, because you're probably familiar with me. Okay, but if the president of the Philippines come to your house, will you use special clothes, for example, barong? Probably yes. Why? Because there is a psychological distance, correct? So that psychological distance that you have, okay, represented by several factors that you put. So those factors represent the features here, the coordinate you put in. Is this clear or not? So
Can
this
we
time,
analyze more than two objects, sir?
yes, of course, you can analyze thousands of objects, but every time you calculate the distance is always between two, right?
Okay.
Right?
Copies.
So you have distance matrix, something like this, okay? So, but every time you compute the distance is always between two, okay? Yes, Roger.
Sir, you've said that we can measure everything. I just would like to ask if in terms of distance, we can measure everything in terms of distance. I would just like to ask if the value of the distance mean, uh, for example, the greater the distance, the shorter the distance, does that mean any further the value of the distance?
Yeah, so I'll give you example. Let me find the uh, example, yeah. Let me get, take for a while. I did not, um, so the value of distance represent just distance, okay? But if you understand this, I will give you example of, okay, so how do you measure the distance between this girl and this dog? What do you think? So distance is just dissimilarity. Okay. So how do you measure that this is fingerprint of one person? How do you measure the face of the person? How do I know that the distance between this monkey and this gorilla? We can compute. Once you get the distance very close, that means they are similar. When the distance is very far, then they are not similar. Then we can measure. Okay? Including the text. What's the distance between Peter and Piotr? You can compute the distance between text, I have calculator there, you can check. Right? So how do you know that this is a plagiarism? Because there are so much similarity, isn't it? How do you calculate similarity? Distance. Is it useful or not? Huh? So how do you calculate that? How do you say that this is similar, these stars? You're talking about the shape, you're talking about the size, you're talking about the color, isn't it? So what do you talking? You're talking about the attribute, the variables, right? So variable of size, variable of colors. At least you have two variables here. Is it clear? The attribute, the coordinate is representing these variables. This is very important concept, right? You're talking about urban planning or architecture. How do you say that this is traditional? Or how do you say that this is good or not? You measure the similarity or dissimilarity, distance. And distance is based on the measurement of type, yeah, measurement of scale. Whether this is ratio type, interval, uh, ordinal or nominal. Can you see that? Is this something new for you, or I don't know, is useful or not, Andrew?
So to make sense of it, are all nominal measurements convertible or transformable to some distance? Is that
Hmm.
one way of
Not only nominal, all measurement scale can be
and
put
ordinal? Okay.
into distance. That's why you can measure anything as long as you can say what is the features of the attribute or the variables. Right, right. So I will skip all the. So usually you will have like this. Say for example this one. Logistic company send package from one city to another. They need automation, and these are the four variables that they put, like the cost, the time, the weight, and incentive. Different units, right? So in that case, see, these are the point coordinate. Yeah, this point coordinate represent the its features. Is it clear now? So when you have four features, yeah, that means you have four variables. Okay, then your coordinate is four numbers there. Okay, now if you want to compute the distance between two objects, then you just input the coordinate into the formula. Is this clear or not? Yeah. So I hope this is clear enough. So there are many other distance that you can discuss more detail. Yes, Lester.
Yes. Hello. I would
Yes.
like to clarify if only the Euclidean distance is the method to measure distance or just one
Okay,
of the
okay,
methods.
okay, okay. This is just one of the method. Euclidean is just one of the method. Okay, I will introduce you at least one or two more so that you can get better understanding. Is that okay? So this is Euclidean distance. This is you just measure the coordinate, right? And then you minus, okay, you square them, okay, and then you sum, and then you take the square root. Okay, so example, yeah, these are the numbers, yeah. So if you want to calculate the Euclidean distance, what you will do, so each of coordinates, so 0 minus 7 square, right? 3 minus 6 square, 4 minus 3 square, 5 minus 1, so plus, yeah. So square, and then you take the square root, yeah. So then you get 9. So this is one of the distance. But remember, Euclidean distance is for quantitative, yeah, either interval or ratio. How about, yeah, this is the, if in reality you have many points, you asked a while ago. Why only 2 points? Yeah? If you have many points, then you compute. Yeah, you will get distance matrix, something like this. Okay, these are the distances between points. Okay, so sometimes you put weight in each variable because maybe cost. Yeah, the cost and time is double important than the weight and incentive. Right. In that case, you put more weight. Okay. So if you put more weight, then so if this is double, so you put weight here, 2, and then this is 1, 1. So instead of 9, now become 12. Clear? Okay. Now I give you another type of distance. This is called Manhattan distance. Usually transportation is using this. Yeah. This is called city block distance. Yeah. So what's city block distance? Similar to Euclidean distance that you commonly use, okay? But instead of square and take the square root, now you only take the absolute value. Okay? So you take the difference and then take absolute value and then you sum. Okay? So I give you the same example, the same coordinate a while ago. What happened if you take city block distance? Okay? So 0 minus 7 plus, this is take absolute value, 3 minus 6, take absolute value, right? And then 4 minus 3, again, you take absolute value and so on. So 0 minus 7 is minus 7. Absolute value is 7, right? 3 minus 6 is minus 3. But you take absolute value, become positive 3. And so on. So the city block distance of these 2 points are now 17. Instead of 9, now become 17. Okay, this represents the grid in the city when you want to travel from one point to another in a city grid. Yeah, we call it Manhattan distance because in Manhattan the city is really grid square. Yeah. Okay. Another example. Okay, this is called Chebyshev distance. This is the maximum value distance. Yeah. In fact, this is the minimum for quantitative. Yeah. How to do? Exactly similar to the city blocks, but instead of sum, you take the maximum. Okay, I'll give you example, the same example. Okay, so 0 minus 7, 3 minus 6, and so on. Okay, so you take the value, but instead of plus, now you put comma here. Can you see that? Okay, and then you take the maximum among this array, cos 7. So the Chebyshev distance is 7 for the same coordinate. Now you get more confused. Okay, now I have the same coordinate I can measure in different type of distance. So which distance I will use? Right, depends on your purpose, yeah. So because each distance have different characteristic, yeah. So if you don't know, okay, and very common, then you use Euclidean distance, right? So if you use Euclidean distance, okay, the shape in 2D will be circular like this. Yeah, this is the characteristic when do you want to use. Yeah. So this is basically flying distance. Okay. If you use a city block, right? If you have weighted, so your square become ellipse. Yeah. If you use city block, instead of concentric circle or concentric ellipse, yeah, your shape will become diamond. Okay. And if you use Chebyshev, your shape will become concentric square. So it's totally different characteristic. If you want to get the minimum among this matrix, okay, for the same coordinate, then you will use Chebyshev distance. Yeah, this one is a game anyway. So Minkowski distance is the generalization, okay, of the metric distance, yeah, in the quantitative. So in this case, you will have parameter, okay. So for example, parameter 3, that means instead of square, now become exponent 3, and then here instead of square root, now you have 1/3 exponent. Yeah. So in this case, you will have 8. So Minkowski distance is generalization of uh, Euclidean, city block, and Chebyshev. Okay, I think I will stop here about distance. Any question? Okay, what you get from this discussion? What did you just learn? Okay, you just you just learn about measurement scale, right? And based on that measurement scale, you can compute the distance. Okay, the distance represent the 1 minus similarity. So based on that similarity, then you can do a lot of many different type of analysis. Yeah, these are the foundation. Okay. So I'll wait if you have any discussion about this topic. Otherwise, we can go continue with the linear programming. Is it okay? Clear? Okay. Good. So you can open the next slide about linear programming. Okay. There is also linear programming lab there. And I would like to remind you the group project presentation, the first group project presentation is next week. Okay, so please submit the slide there in Moodle. Yeah, before the 1 day before the presentation, yeah, before the class. Okay. Okay, let's go to the topic. And this is a very long slide. I hope we can finish. Okay, so now this is the title supposed to be a linear programming for planners. Yeah? So urban planning is often seen as art, right? A mixed design, sociology, and politics. But today, yeah, we are going to talk about the science of planning. Okay, how you will optimize. Yeah? Especially, how do you make decision when you have limited resources, yeah, limited money, limited decision, limited land, limited, and you have conflicting goals. Okay, so this is practically what is called optimization tool. Okay, so by the end of this lesson, I hope you can comprehend what is linear programming and how do you use solver, yeah, in Excel. I have also computed there in. If you don't have Excel, you can also use in the web, yeah, and we can compute sensitivity analysis. Yeah. Okay, So these are the topic. Yeah? I think I have 7 topics here. So the motivation, the vocabulary, yeah, and then I introduce you the virtual lab, okay? And I will discuss about shadow price or the value of limit, and we discuss about sensitivity analysis, and then I hope we can have um, more discussion, okay, and practice, yeah, at the end, yeah, custom workshop, okay. So let's go to the first part, yeah. So why planning is hard? Hmm. It's not because we don't have good ideas, yeah, but because everything is connected, isn't it? So if you build more housing, the traffic get worse, yeah. If you preserve the green space, the housing price goes up, yeah. If you, because you have limited resources, you have limited budget, you have limited land, okay. So, and we as human, okay, are very bad in juggling, say, 50 variables at once. Okay, so we usually focus only one or two, yeah, and hope for the best, isn't it? So we have too many stakeholders, yeah. So it's a completely complex. So traditionally, okay, how do we solve this problem? Yeah, we sketch a few options, say option 1, alternative 2, alternative 3, and so on. And then we argue in the meeting, yeah, isn't it? So usually, uh, hippo, you know what is hippo? The highest paid person opinion. Yeah, this is dangerous. You know? So how do we know that option D wasn't better? Yeah. Just because someone said the loudest voice, usually they win. Yeah. So they rely on intuition, but intuition usually fail when the numbers get big. Yeah. Okay. So then the new way of doing this is actually called optimization. Okay. So you need to learn what is optimization. Optimization is different. We don't guess. Yeah. We describe the problem into computer. So computer understand mathematics. Then you need to put the mathematics inside that computer. Okay, it will check millions of possibilities in just a few seconds. Okay, so what we are doing, we are moved from subjective argument to objective answer. Okay, so remember, yeah, the input is messy, but the output is clearly the optimal path. Yeah. So I want to introduce you one specific tool, yeah, in optimization. And usually this is like the beginning of optimization. Always learn about what is called LP or linear programming. Yeah. Don't let the word programming scare you. Okay. So it just means planning. Yeah. This is an old 1940s name. Yeah. In the context in 1940s, programming means planning at that time. So it doesn't mean coding. Okay. So what is LP or linear programming? It's just a method, yeah, finding the best outcomes. For example, maximum profit, minimum traffic. Yeah, assuming that the rule are very simple and straightforward, just linear relationship. Okay, and then if you double the house, it double the tax. So that's linear. Okay, so when we say the best outcome here, that means either you maximize the profit, yeah, or revenue, or you minimize the cost. Yeah, or over this course in one semester, we always use exactly similar technique, yeah, maximize and minimize, okay, optimization in this class. And then what do you mean by linear? Yeah? Linear mean straight line. Yeah, it's very simple rule. Okay, so linear programming is something like this. Okay, you will have both constraint and objective function you put in, and the constraint must be linear and the objective must be linear also. Yeah. When you put in both, okay, the program, yeah, will do an algorithm called simplex method. Yeah. This was invented in 1940 by Danzig. Okay, and then the program will search for, will form the feasible region like this, and then it will find the best, the optimal solution. Yeah, and at this point, okay, yeah, it has been used in many fields, yeah, including transportation and urban planning. So it was formulated first in 1947 in a way to find the massive manual program activities for the war, yeah, logistic operation. Yeah. Now, linear programming is one of the major optimization technique. Okay, so I will not discuss the numeric in here. I will just discuss how you will transform your problems, okay, into linear programming, and then you just use the calculator, okay, and understand the meaning. So the ingredient of LP, this is what you need to remember. Yeah, this is the mental model for the whole course. And today, so remember nothing else. You must remember these three. Yeah, decision, goal, and limits. Yeah, so every optimization has three parts, three ingredients. Number one is the decision. Yeah, the decision variables. These are the knobs that you can turn. For example, number of houses, the road width. Yeah. What can you change are the decision variables. Okay. Yeah, the decision, the goal, and the limit. What's the second? The goal. Yeah. The goal, what do I want? What does success look like? Is it more money? Is it less CO2? So, yeah, what is your objective? And the third ingredient is the limit. You never have infinite money, right? You never have infinite land. So these are your constraints. What stop you to reach your goal? Yeah. Can you remember? Okay. The decision, the goal, and the limit. Yeah. So, okay, let's try with this simple example. Say you have $10 million. Yeah, this is your budget limit. Yeah. So you want to move maximum number of people. And you have two options here. Yeah. Either you invest in bus or in rail. Okay. The bus have got cost of 1 million and the rail have cost of 5 million. Okay. And these are the capacity, yeah, passenger per lane. Yeah. Question. Do you buy 10 buses or do you buy 2 rail cars? Or is it a mix? Yes. 2 rails? Probably. Okay. So basically you have a trade-off, isn't it? Okay. So you need to find the specific mix that give the highest capacity, yeah, without breaking the band, yeah, the money, the budget. So yeah, this is very simple, right? So if you have two rails, you get 2 times 400 become 800 passenger per lane, right? So if you have if the same for 10 bus, so you for 10 million you get 10 bus, so that means 10 times 50, so you get 500 passenger per lane. So in this case, correct, yeah. You said that a while ago. Leicester, yeah. So you get the winner is rail. Yeah, very easy. Yeah, but this is just to set the stage for the harder problem later. Yeah. So our tool, okay, yeah, you can click that in the slide. Yeah, then you will see the optimization. Yeah. Well, yes, you may be thinking I did not sign up for math class. It's good news. Yeah. So we are not doing the mathematics here. Yeah, we are just using the tool. Yeah. There's a virtual lab that I have made. Okay, so your job is to describe the problem, your story. Okay, and the tool job is to crunch this number. So using this online uh, calculator. Yeah, it's free, it's powerful, and it's visual. Okay, so no math required, but you still need to create the math. Yeah. So example a while ago, right? So you put 50 bus plus 400 rail. Can you see that a while ago? This one, yeah. 50 and 400, right? So you will put that 50 bus and 400 rail. This is the objective that you want. Okay. And then subject to uh, bus plus 5 rail is less than 10, isn't it? Shall we try this? Yeah. So if you try this, it will give you exactly the answer. Yeah. Something like this. Okay. Let's try this live. Right. So what you will do, so you type here 50 plus, yeah, plus 400 rail. Or if you want, I can put rail or something. But if you don't, you just and then you remove all of these, right? Then bus plus 5 rail should be less than equal to 10. Don't forget to put semicolon. Yeah. So, and then you can add, if this one is done already. Yeah. As simple as that. See, got that. If you want, you can also add additional that the bus must be larger or equal to 0, semicolon, and then the rail is also must be larger or equal to 0. Yeah, these two are optional. Okay, it will give you exactly the same. Okay, I will let you try so that you will know. Is it clear or not?
Okay.
It works? So given the problem, okay, you need to put into objective function and then the constant function. Yeah. Then solve the problem, you will get the result here. You see? Any question? Yes, Corinne.
Hi, sir. I have a question.
Uh-huh.
This is not actually the coding type of question, but I would like to ask, when do we apply or include linear programming in planning or design? Because from what I noticed from private developers, especially in planning township projects, is that they actually do benchmarking first, then identify modes of transportation, but they do not consider doing linear programming or doing feasibility studies first. So, in the middle of the planning stage, it results into a some sort of a problem, because it turns out that the proposed modes of transportation that's going to be implemented or used in that township project is costlier than the expected outcome.
Okay. So it's a good question. When are you going to use this
Yes, because
LP,
this,
right?
from what I noticed, sir, they do list first or have a preferences. For example, in a township projects from my office, they suggested to have BRTs, um, buses, and other modes of transportation, but they do not um, use linear programming.
Yes, they
It
don't
comes
use
last.
it comes last, correct. So once you have uh, something that you want to optimize, for example, you want to do scheduling, you want to basically linear programming you will use when you have limited resources and you want to either maximize the profit, yeah, or the gain, or you want to minimize the cost. Then you use this. The one that you just told me is later we'll discuss, yeah, during prioritization and multi-criteria decision making. Yeah, that's another topic that we will discuss in our class, right? But at this point, when we discuss about linear programming, okay, remember this, yeah, you have certain objective that you want. You want to maximize something, or you want to minimize something, subject to certain constraint that you have. And this objective and the constraint must be linear. Okay. So if you have that, then you can use this. Okay. George, do you want to share your screen?
Sir, I get it now. It's working
Oh, you
now.
got it.
Yeah,
Okay.
yeah.
What was the problem?
The space between this
Okay.
equal. So there must be no space between this wait, sir, I'll check it again. This less than or greater than should
Yeah. Okay.
there must be no space between this equal sign and this greater or less than sign.
Oh, no, you can put space, no problem. You see, in my case, I put space, no problem.
But for me, sir, when I remove the space, then it works.
Okay.
Yeah.
So it's just a parser problem. This one, I put space, no problem. Yeah. This one, probably you need to multiply like this. You can also do the same. Okay, let's continue first. Probably after certain part, maybe part 3, you will understand it better. Okay, so at this point, I'm just introducing this. Can you see my slide? Okay, so let's go to part 2 first. Yeah, I will go to the detail of the ingredients. Yeah, so the first ingredient is decision variables. Yeah, so ask yourself, what do I have control over? For example, in a zoning meeting, okay, you cannot control the price of the steel. Yeah? That's a fact, right? So then you cannot, but you can control how many hectare of land that you assign to a commercial use. So anything that you choose, yeah, something that you can control, okay, that is part of your decision variables. And then you can name them any. Yeah? For example, I can name them X, Y, Z, or A, B, C, or even rail and bus and so on. Okay, and so on. So sometimes we name it very simple like this X, Y, Z in here, so that to save space. Yeah, so that not so long. And don't put, for example, area of park. Okay? That is a space between area of park, that will not work. Yeah? Or the number of bus, it will not work because you have space there. So you need to put underscore to make it work. Yeah. So planner often confuse the goal, which is to make people happy, with the variables. Yeah, which is to build 3 parks, for example. So in this case, you must strictly define variables as the input that you can control. Okay, I give you an example. The rule is simple. If you cannot control it, it is not decision variable. Yeah. These are example. In zoning, you have variable of area of residential, yeah, area of commercial. Yeah. In traffic, for example, you have green time in seconds or red times. In housing, how many number of apartment, how many townhouse. Yeah. A while ago, you are talking about the public transport, how many buses, how many rail, and so on. Okay. Decision variable must be quantitative, not nominal, not ordinal. Okay. Must be quantitative. So let's practice so that I know this is you understand or not. So what are the decision variable of this scenario? Say, can you read this scenario? Yeah. So we need to design a parking lot. Yeah. We can paint the space for compact cars or for SUV. Compact space, save room. But SUV space, charge higher fees. So my question is, the profit and the space are decision variables? So what are the decision variables? Anyone? Yes, Thomas.
Sir, probably the number of compact cars is spaces for cars versus spaces for SUVs.
Very good. Yeah. So it's not the profit. Yeah. The profit is the goal. Okay. So the spaces are the thing that you can control. Okay, so the spaces become the input, yeah, decision variables here. Very good. Okay, so let's go to the ingredient number 2, yeah. So ingredient number 2 is the objective function. This is your North Star, right? So you may say, I want a good project. Well, you need to define what is good project. Yeah, for example, I want to minimize the waste. I want to maximize the profit and so on. Yeah. So what is the definition of success? Yeah, put it in mathematics as a function, as a linear function, something like this. So you want to maximize the profit, yeah, consists of the decision variables x and y, okay, and then or minimize the cost as the function of the decision variable ingredient number 1 a while ago. Is it clear or not? Yeah. So the function of objective function here is just the score. Okay. So, and you have only one objective at one time. Yeah. In linear programming, you can either maximize or minimize at one time. You cannot have both. Yeah. In linear programming. Yeah. So let's take example. So we earn 10K tax for residential and 30K for commercial. So residential is X, commercial is Y. Yeah. The number of unit of residential is X, the number of unit for commercial is Y. Okay. So what is the objective function? Maximize or minimize? Yes, Lester.
Maximize, sir.
Yeah, maximize what?
Maximize the income or profit for the tax in residential and commercial spaces.
Right. So you need to add, okay. So
10
10 times
X
X plus
plus 30Y.
30 times Y. Okay. So this is the objective function that you, is it clear or not? Yeah. Yeah. Very good. Yeah. Next, another example. So the parks cost $50 to maintain. The garden cost 20. This is cost. So you want to minimize or maximize? Yes, Roger. I cannot hear
Minimize,
you.
sir.
Minimize, yeah, because this is cost, not revenue. So you want to minimize. What do you minimize? Okay, so you put 50 times X,
X
okay, 20
plus
plus 20 times
times
Y.
Y.
Okay, easy, yeah? Is it easy or not? Okay, so first ingredient, you need to check the variable that you want to decide, yeah, decision variable. Number 2, ingredient number 2, you define the objective, yeah, either maximize or minimize. Is it clear? Very simple like that. Yeah, multiply the value with the variables, and then you just add. Okay, simple, yeah. Okay, so the word earn implies maximization. Yeah, the word cost implies minimization. Yeah, so the numbers here are just stick to the variables. Yeah. Okay. Very good. Okay. Simple. So this number represent coefficient. Yeah. So I just put it without scary word. Yeah. So it's just the price. Next. Okay, let's practice again so that you get better. Okay, now your turn. So we want shape. Yeah, you are planting trees to cool the city. The number of oak, X, provide 5 units shade. The number of pine, Y, provide 3 units shade. You want to maximize the shade. So step 1, maximize or minimize? It's already said, maximize. Yeah. So why? Is shade good or bad? Good. So in that case, we maximize. So can you write the equation? Yes, George. You want to write it here? You can write it here, right? I think you can write in this Zoom, or you can type in the chat. Yes. 5x plus 3y. Very good. Yeah. So George and Lester. Yeah. Very good. Easy, yeah? Okay. Good. So you know the objective function. Okay. Now we go to the third one. Okay. The constraint.
Sorry, sir. I thought
Yes.
my mic is on. I'm talking while I'm writing the equation, but my mic is off.
Your mic is
Okay.
off, yeah. But
Yeah,
you
sorry,
write
sir.
it. That's
Yeah,
no
yeah.
problem. Yeah, no
I'm
problem.
talking while I'm doing this equation.
That's good. That's good.
Yeah, okay,
But
sorry, sir.
at least you
Okay.
get the
Yeah.
result. Okay. Thank you. Okay. So the third ingredient is the constraint. Okay. Okay. Let me clean up this one, right? Okay. So in the constraint, yeah, without the constraint, the answer will be how much profit can we make? It will be infinity. Okay. Without constraint, everything seems nice. Yeah. It's an ideal. So constraint is the one that bring back us to reality. Okay. So for example, you run out of land, you run out of money. Yeah. So this is the law that stop you. Constraint usually are inequalities, less than or greater than. Okay. So this is the reality check. Yeah. So you constraint usually have format like this. Left hand side, usually the variables. Okay. If less than the right hand side, these are the limits. Yeah. Or larger than. Okay. So usually you have two type, yeah, or three type of constraint. Yeah. The first type is the resources. The second type is the policy. Yeah. And the third type is actually the boundary. Okay. Let's say the first type, yeah, the constraint type A. This represent the resources, yeah. So you have the budget limit, you have the land limit, right? You have the people, number of people limit, and so on. So the resources always have limit. So these are the most common constraint, yeah, resource constraint. So you have a bucket, but it only holds so much. Say, huh? Uh, say you have 20 hectare land in total, and your residential number of residential units and commercial unit is Y, yeah, will use that land. So how are you going to do? Yeah, X plus Y is less than 20. Clear, yeah? Right? So together, they cannot exceed 20. Is it clear? Can we use 19? Yes. Can we use 21? Cannot. Yeah. So together between residential and commercial, the sum must be less than 20 hectares that you have. So the sum of the part must be less than the whole. Yeah, this is very fundamental equation in planning, isn't it? You always have limit. Huh? Now, the second type of constraint is your policy, your law, yeah, your design rule. Yeah, this is policy constraint. Yeah, this is not physics. Yeah, the resources usually physics. Yeah, so this is the law. So the city council said you must build at least 5 hectares of housing. Yeah, this is the law. So then at least that means what? Greater than. Yeah, you flip the sign. Okay, so it's no longer the ceiling, yeah, less than, it is the floor. Yeah, so greater than or equal. Okay, so you can build 5, you can build 6, 7, 20, yeah? But you cannot build 4. Is it clear? Okay, let's practice again so that you can get the idea. Say we need to double the number of pines compared to the oak. Can you write the constraint equation here? So each oak, X, costs 100. Each pine, Y, costs 50. Your total budget is only 1,000. So, anyone want to write here? Okay, write it in the slide. Yeah, George, you can do it. Okay, so the clue is you double the number of pine compared to the oak. Yeah, go ahead. 100 X plus 50Y is less than 1,000. Okay. Okay. Very good. Yeah. So you have that. Yeah. Is it clear? Yeah. So if I have 1 oak, I need 2 pine. So this constraint, okay, you can simplify, okay, into y larger than 2x. That means y equal to 2x in the ratio constraint. Yeah, so this is called ratio constraint. So the budget is standard, but the ratio constraint is a little bit tricky. Yeah. So I just want to introduce this here. Okay, the third type of constraint, yeah, usually hidden, the boundary constraint. Usually we say non-negative. Yeah. So the program there is already have, yeah, the calculator will assume this, so but you need just to know that this exists. Yeah, so each of this decision variable must be positive or 0. Yeah, so okay, this is the hidden rule in urban planning. Yeah? So you cannot unbuild the building that does not exist, isn't it? So you cannot have negative distance. Yeah, so this non-negativity, yeah, you tell the computer that x larger than 0 or y larger than 0. Yeah. Otherwise, the math will tell you need to build negative 1,000 houses, yeah, to save money. Yeah, computer does not know. So yeah, this is funny but necessary slide. Yeah. The calculator does not know the physics, yeah, unless we tell them. So this is how we tell them. Okay, as the summary, yeah, of the jargon, Yeah, remember this, yeah, in English, yeah. If your client said, I want to maximize the profit or benefit, so then you maximize Z here is the objective function, yeah. Or you want to minimize the cost, yeah, or minimize the waste, so you minimize the objective function. In the constraint, yeah. So if you cannot exceed, yeah, or limit the budget, so you have a budget limit, then you see less than or equal, yeah. So example is cost is less than the budget. Okay? If you see at least minimum requirement, then you say greater than. Okay, housing is larger than 500. If if the client said must equal to, then of course equal. Yeah. So capacity cannot exceed. That means less than, yeah, the number of cars less than the capacity. Okay. So if you said we need a minimum of, yeah, green space, yeah, say 10 hectare. So that means greater than, yeah. So if you say double, then it's a ratio. So you can just put this value. So this is the cheat sheet. Yeah. So I hope you don't get the sign wrong. Yeah. Because if you get the sign wrong, you will get a wrong plan. Is it clear? So remember this, yeah. Every optimization problem, not necessarily linear programming, yeah. Every optimization problem consists of 3 ingredients. Yeah. So if you are stuck, identify these 3 things, then you will be in control. Yeah. So first is decision variables. Yeah. It's the things that you can change, you can control. Okay. The second is the goal, the objective. Yeah. This is the definition of success. Yeah. Either you maximize the benefit or minimize the cost. Okay. And the third one is the constraint, the limit. Okay. Something that stops you to achieve your objective. Yeah. Very good. Yeah. Okay. So the constraint, you will have inequality or equality. Yeah. So objective must be maximized or minimized. Is it clear or not? Simple. Okay, let now go to part 3. Yeah. So this is the virtual lab a while ago. I want you to understand, okay, using a very simple mixed land use dilemma case study. Okay. So this is the challenge. Yeah. So you design a new city district with conflicting need. Yeah. The status is undeveloped land. Okay. So we are going to solve a real planning together. Yeah. Planning problem. Imagine you are the chief planner of the new district here. Okay. You have the empty land and you need to zone it. Huh? Of course, the mayor wants tax money. Yeah, and the citizen wants housing. Yeah, and the engineers worry about traffic. Okay, so let's see how we can make everyone happy. Okay, simple, yeah. So let's start with the story. This is the data. Okay, here are the facts. Okay, if you want to do linear programming, you need to have this fact first. Yeah, yeah, similar to this. So write this down. Okay, write this down. So the commercial pay more tax, say 30,000 per year, okay, per hectare, compared to residential, which is only 10K per hectare. So maybe your instinct, if you use your instinct, you will build only commercial. Okay, but look at the massive traffic. Okay, the commercial will have 100 trips per hectare, while residential is only 20 trips per hectare. Oh, okay. We have a law now also that you must have at least 5 hectares of residential. And then in terms of the land, you have the limit. The total area available is only 20 hectares. Now, this is the client's brief. Okay. So it contains all the numbers that you need. Can you start to create the optimization problems in math? What are the variables? The three ingredients. Yeah. What are the decision variables? What is the objective function? And then what is the constraint equation or inequality? Can you start? Okay, I give you time. How long do you want to think about this first? Okay, 5 minutes. Yeah, you think about the mathematical equation that you will put. Yeah, the variables. Okay, and then the objective and the constraint. Yeah, and then we will discuss later. Okay. Yes. What is, oh, 5 minutes. Yeah, okay, 5 minutes. 22. It's done. It's done. Okay, let's come back. Oh, I still share. Okay. Okay, so step one, yeah. So ingredient. The first ingredient is decision variable, yeah. So what can we decide? Yeah. In this example, yeah, you have two, yeah. Possibility is residential and commercial, isn't it? So in that case, X is the hectare of residential, and then Y is the hectare of commercial. Okay, simple. Okay. And second ingredient is the goal, isn't it? So this is the objective. You want to maximize the tax revenue. Okay, so remember residential pay 10K per X, yeah? While the commercial pay 30K per Y. So in that case, you want to maximize the tax, yeah? It is 10X plus 30Y. Good. Okay. And then the last one is the uh, constraint. So you have three constraints here, yeah, based on the sheet a while ago. So you have land constraint, traffic constraint, and the policy constraint, yeah. So the land constraint total less than 20, so plus. And then the traffic, depending on the rate, yeah, the trip rate here for each land use, right? Should be less than 800. And then this is a policy, so must be larger than 5, yeah. So this is our model. So you put in the lab, you supposed to get something like this. Okay. And when you put it in the lab, you're supposed to just type, yeah, something like this. Yeah. So you can, don't forget the semicolon, okay? And you select maximize the objective function, okay? And then subject to these three constraint. Yeah, don't forget the semicolon each at the end of each constraint. Yeah, so no need to add extra word. If there is a syntax error, so then this is the first problem. Okay, let's check this. So I want everyone in the correct page. So can you share your screen then? Yeah, each of you, just a brief so that I will know you are okay. Go ahead. Okay, good. Super. So you get 15 and 5. Is that correct? Go. Next. Yep. Super. Next. Okay, good. Wait. This is strange. Wait, can we use? I think you miss one constraint. I think you miss one constraint. Is it? So 20, 100. Oh, this one. This one not plus. This one equal. Less than equal to 800, not plus. Can you correct that? Yes. Yeah, there. Good. Next. Who's next? Yeah, this is correct. Okay, Emilio, that is correct. Next. Good. Who's next? Yeah, so you get the visualization correctly. Okay, next. Everyone share the screen already? Okay. Yeah, Roger, you want to say something? Oh, Paul.
Yes, I have a question.
Oh, go.
Is it necessary to have the constraints for y would be greater than or equal to 0? Would there be a chance that
No
for
problem. You
this?
can add that one. So x larger than 0 and then y larger than 0. Okay, you can
Mm,
add, but the calculator already assumed that inside the program.
oh, okay.
Okay.
Are there any problems in the future that would involve negative values for the variables? But
Uh,
because
yeah,
for
it
this
is it
case,
is possible. It is possible that
okay, okay.
so if your problem is actually can be negative, the decision variable can be negative, then you cannot use this calculator. You can use Excel.
Okay. Thank
Yeah,
you, thank you.
Excel solver. There is a possibility of that. Okay.
Thank you, sir.
Yeah, thank you. Yeah, Thomas, you want to share your screen? Okay, good. This is correct. Yeah, very good. Daniel, you want to share your screen? Yeah, George, very good.
Sir, I sent an image on the chat. I cannot share a screen because I'm on a phone, but I am also on my PC.
Oh, okay. Okay, so everyone share screen for it, finished? Good. Okay, let's continue then. I will share my screen then. What happened? My slide. Oh, there. Okay, there. Yeah, you get something like this, right? So this is the visual representation of our city dilemma. Okay, so uh, yeah, this is the syntax guide. Yeah, so there is a parser inside that calculator, which is quite strict actually. Okay, so you want to maximize, yeah, or minimize. So some number and then the variable plus, yeah, some number another variable subject to constraint, yeah. So number multiplied by the variable plus or minus, yeah. Number multiplied by the variable less than or larger than, yeah. So do not use comma in the thousand, okay. And then variable as much as possible use single letter, yeah. And then without space, yeah. So if you put number, that's okay. So x1, x2, x3, that's also okay. So if you ask about, Roger was asking about non-negative constraint, yeah, it's not needed, but because the tool add automatically. So you will have something like this. What is this pink color? Yeah, this pink color represent the path that the simplex is searching. Yeah, this is the searching of the path from 0, 0, and then simplex go to this first point, and then second point, and then finally reach this point, which is the optimum value. Okay, so this is involves some searching. So you can go in that calculator and then go up there. Instead of simplex, you can use interior point, and then it will go directly a different path. Yeah, so different algorithm will create different path. Okay. Now, if you go down, yeah, there is also what is called feasible corner points. Yeah, these are the coordinate of the corner point here. Can you see that? Yeah, and the one in green here is the feasible region. Yeah, these are feasible. Yeah, where the rule, the constraint rules are obeyed. Yeah, these are the legal plan. Yeah, but if you go out of this constraint, yeah, these are illegal plan. Yeah, too expensive, too much traffic, illegal zoning, and so on. Okay, usually, yeah, and okay, the optimum value is on the edge of this visible polygon. Okay, and usually in the corner. Okay, so every point inside this polygon is a legal city plan. Yeah, it will fit the land, it will fit the traffic, it has enough housing. Okay, so you can put any point here, they are legal. Okay, yeah, under the constant that you set. Okay, but not necessarily optimum, isn't it? So you will pick a point, yeah, with this within this boundary, yeah, to make it optimum. Okay, but if you pick a point outside of this polygon, yeah, you are either breaking the law or either breaking the physics. Yeah, yeah, you are at the limit of the resources. Is it clear? Okay, so this one, yeah, this is the polygon of legal plan. I hope this is clear enough. So now, which line, which? Yeah. So let's discuss more detail on each line. Okay, so that you will understand. Okay, so see the vertical line here. Okay, this one. This vertical line, what is this? This is x larger than 5, right? What is this? X larger than 5 is the policy a while ago. Yeah, the residential must be larger than 5. Can you see that? Okay, that is our housing policy. Yeah, you cannot go on the left of that, right? So now, can you see the steep line chopping? Go off of that top. Yeah, this one, the green one. Yeah, this is the traffic, right? The steep cut here. The green one represent the traffic, and the red one here represent the diagonal cut here represent the land constraint. Yeah, yeah. This green represent traffic bottleneck. Is it clear or not? Yeah. All this line represent the constraint that you set a while ago. Okay. Now, the traffic, yeah, the green here, cut with the red one, right? So the traffic cut with the red one, yeah. So this is represent high commercial option, yeah. So here, so the optimum here, the value of optimum here happen when this line, the green, the traffic line, meet with the land constraint. Okay? They are not happen here in the green and blue, right? But it happened the optimum value in this example happen in this intersection. Okay, so now go to the corner point, right? So the calculator also check the corner point. Okay, what is the meaning of 0, 1? And these are the corner point, right? And these are the value of the objective value, yeah, z at that corner point, yeah. 50, that minimum housing, no commercial at all, right? 20, that means maximum housing, no commercial at all. Okay. 15.5, that is a mixed land use between 15 housing and then 5 commercial. Okay. And 5.7 is the minimum housing with maximum traffic. Okay, so if you look at the drawing, so you will see the corner, what's the meaning. Okay, I hope this is clear enough. Okay, so why the corner? Why the corner are special? Yeah, imagine you are in the dark room, okay, looking for the hottest spot. Okay, you keep walking toward the heat. Okay? You won't stop in the middle of the room, right? So you keep walking until you hit a wall. Then you slide, yeah, similar to this simplex movement. You slide, yeah, along the wall, right? Okay, until you hit the corner. Yeah. So optimization always push to the extreme limit. Yeah, this is the intuition of simplex method. Yeah, so we don't settle on the average. We always go to the extreme. Yeah, so if something is profitable, why we should stop there? We should go more of it until we hit the wall of the constraint. Yeah, that's the logic, isn't it? So if you use interior path, you start from the middle of the polygon and then go directly here. Yeah, go to the optimum value. It will get exactly the same. Yeah, so different algorithm, different path of search only. Okay, and the winner is that point. Yeah, 15.5. Yeah, what is the meaning of 15.5? Yeah, 5 hectare for housing. Okay, and then 15 hectare for housing and then 5 hectare for commercial. So what is the total profit? Yeah, you just input to the objective function. Yeah, so 10 times 15. Yeah, and then plus 30 times 5. This is the amount of tax. Okay, so this is 300K is the maximum tax that you can get from this district. Yeah, this is mathematically the best possible city we can build given the rule. Clear, yeah? So that means now you have the strategy, right? So you max out the land with this 20, right? Because 15 plus 5 is 20, right? And you max out the traffic also. Yeah, because 300 plus 500 is 800. Yeah. And you also satisfy the policy, yeah, because 15 is larger than 5. So in conclusion, yeah, we fill the bucket perfectly, no waste of land, no waste of road capacity. Okay, so we didn't waste a single square meter and single car trip. So it's a very tight design. Yeah. So tightness imply efficiency. Okay. Be careful when you do overly optimize like this, yeah, because there is no redundancy. It is not robust. Yeah. If something happen, and then it will have domino collapse. Okay. So yeah, you get this line connected with the traffic, right? So the traffic connecting with the land constraint. Yeah. Okay. So raise your hand if you get 300. You get exactly the same, right? So now, yes, very good. Okay. So now look at the plan. Okay, we are limited by traffic, right? So if we widen the road, could we build more commercial, which pay more? How much more? Yeah. So that's exactly the next question. Yeah. What if we widen the road? Will we make more money in terms of the tax? Yeah. This lead to what is called shadow price. Yeah. This is, you can search in Google. Yeah. Yeah. This is the most valuable part for the professional. Okay. So let's go to part 4. Okay. So are you ready? Yeah. This is the value of the limit. It's called shadow price. Okay. This is a little bit more sophisticated. Yeah. Because we are interpreting what is called the dual of the simplex method. Yeah. How you make the investment decision. Okay. So this is the economic value of the constraint, moving from solving the problem to strategizing. Yeah. Okay. So we just find the answer a while ago, right? 15.5. Yeah, 15 housing, residential, and then 5 commercial, which is great. But your job isn't just to fill the bucket. Yeah, it is to decide if we need a bigger bucket. Now we are going to ask a strategic question. If I have 1 million to invest, do I buy land or do I build road? Ah, right. Okay, now you have the budget, say additional 1 million to invest. Okay, what you will do? Yeah, planner that don't just follow the rule, right? Planner change the rule. Yeah. Okay, so if we bought more land, what will happen? If widen the road, what will happen? Okay, which change give the biggest ROI? Right. Okay, is this interesting enough? Okay, so imagine you are running toward the pile of money. What stopped you? Huh? Was it the wall on the left or the wall in front? Yeah. The wall you physically touch is called binding. Yeah. In our solution, remember this, yeah? We use all the land, we use all the traffic capacity. Yeah. those are binding. Okay. Do you understand? Okay, I'll come back to the guess what? The optimum value here, the star, okay, happen when the traffic intersect with the land constraint, right? The traffic constraint, the green, and then the land constraint, the red. Yeah, not about the policy constraint. So it happened between these two constraints. So these two constraints is called binding. Clear? The policy constraints are non-binding. Yeah, the one that you see in the calculator there, can you see the dual there? Yeah, you will see binding or non-binding. Okay, so now look at the policy. Yeah, the policy is x larger than 5, isn't it? So the law said build at least 5 houses. We build 15, right? In the optimum value of 15, not 5. So we clear the hurdle easily. Okay, that means you have slack, 10 units slack. Yeah, so you actually build x is 15. Okay, so 15 minus the requirement, it is 5, you have 10. Yeah, so this 10 unit is called slack. So if the mayor lowered the requirement at least 3 houses, yeah, does it change our plan? No, because we are already at 15, right? So the policy is irrelevant now. Okay, so relaxing this rule have nothing because we already satisfy this easily. Yeah, this is about prioritization. Yeah, so don't spend your political capital fighting for a rule that actually isn't hurting you. Okay, you don't need to propose the new law to make it 3 instead of 5. Clear, yeah? Next, this is the most important concept in this course, yeah? Shadow price. It asks, if I have one more unit of resources, example, one more hectare, one more car trip, yeah, how much richer would the city be? Yeah, so it tells you the exact value of expanding your limit. Yeah, this is the secret weapon. Okay, this is the most important number in planning. So the definition: if I get one more unit, more resources, yeah, how much profit do I make? Yeah, if you are maximizing, you are talking about a profit. Yeah, if I'm forced to deliver one plus more unit tightening, how much does my cost will increase? This is another way of thinking. Yeah. So if you want to minimize, then if I reduce the requirement by -1, how much money do I save? That's the actual meaning of dual price. Yeah. So you just get one of these that serve you better. They are actually the same meaning. Yeah, different optimization, maximizing or minimizing. Okay, so let's stick to the green one. Yeah, you are maximizing. So in that case, if I get one unit more resources, how much more profit do I make? Okay, so dual shadow is the marginal value of the resources. Okay, so when we minimize the cost, okay, then of course the shadow price become price tag of the rule, yeah, or price tag of the policy. So if the shadow price of a green space requirement is 1 million, okay, it means asking you for one more hectare costs city 1 more million. Yeah, it will help you to negotiate, right? Is this extra hectare worth 1 million? Yes or no? Yeah. If not, you lower the requirement. Okay. I'll give you more example, okay, so that you can understand this. Yeah. How to find the shadow price first? Yeah. So you go down to the interpretation of the result. You will get something like this, right? And you see that? So your maximum value is 300. Yeah. I think this is the old version of the calculator. Yeah. So you will see the binding or non-binding. Can you see that? Binding mean the one that make the intersection, yeah, the constant that make the intersection. Okay. And this is the shadow price. Yeah. This is the shadow price. 5, 0.25, and 0. Yeah. So 5 here is the shadow price for land. And 0.25 is the shadow price for traffic, and 0 is the shadow price for policy, right? What does that mean? Yeah, so that's the question, right? So let's interpret the meaning, yeah, of the dual of the shadow price. Okay, so the value of the shadow price means the profit gain after adding one more unit of the constraint. Okay, so if the value is positive, yeah, the constraint is binding, then you invest here. If the value is 0, that means the constraint has slack, have some leftover. So don't invest there. Okay, so let's check one by one. Okay, let's interpret the this is what you get, I think. Is that correct? Yeah, the sensitivity report, you will get something like this. Now you get the table. Okay. So 5, 25, 0.25, and 0. Okay. So say the first constraint, the value is 5. Yeah, the first constraint is the land, right? Yeah. So the calculator said the land worth 5 shadow price. What's the meaning of that 5? That 5 represents $5,000 per year. Okay. Now, if your neighbor offer to lease you a hectare land, right, for $2,000, will you take it? Yes. Yeah. You pay 2,000, you get 5,000. So you make 3,000. Yeah. But if they want 10,000, will you take it? No. Yeah. You walk away. Yeah. The math prove you this is a bad deal. So I hope you understand. By knowing the shadow price, you know the decision, okay, to buy or no buy decision for the land. Is this clear or not? Any question? Okay, maybe you will understand better for the next shadow price. Yeah, 0.25. What is this? Constraint 2, which is the traffic, right? So the traffic 0.25, that means 200 multiplied by 1,000, right? So $250. Yeah, that's the meaning, right? So one extra vehicle trip per hour capacity is actually worth $250 in annual tax. Yeah, this sounds low, right? But remember, the road handle hundred of cars, isn't it? So if you add 100 trips per hour, so that means 100 times 250, that easily become $25,000 of value. Say, yeah, after you compute the cost of building the road, it costs 15,000 to widen the road. Okay, the cost is 15,000, but the benefit is actually it will improve by 100 trips per hour. So that means 25,000. So 25,000 is larger than 15,000, isn't it? So the project is approved. Yeah. This is the urban planning application. Yeah. You can compare the infrastructure costs, this one 15,000, with the benefit, the economic benefit. So shadow price represent the economic benefit. Is it clear or not? Is it something useful? Okay. The third constraint is a policy, right? At this point, you get zero, isn't it? What is the meaning of this? Why policy worth zero? Yeah, because it is non-binding. We aren't hitting the wall. Yeah, so the mayor spend political capital to if the mayor spend political capital to lower the housing requirement, say from 5 to 3, yeah, it just waste of his time. Yeah, it adds $0 to the tax base because we wanted to build 15 house anyway. Clear? Yeah. So knowing the shadow price, you know your decision. Okay. So if it is non-binding constraint, yeah, usually you have shadow price of zero. So don't fix what isn't stopping you. Is it clear or not? Any question? Okay. So once you understand the meaning of shadow price, okay, let's get another example here. This is another example of shadow minimization. Yeah, totally different from earlier. Yeah. So if you require a developer to build at least 100 affordable units, this is a new problem. And then the objective is to minimize the construction costs, and you have the shadow price of 50,000. Okay. Then what the meaning? That means every time you force the developer to build one extra unit, say from 100 to 101, okay, so the total project cost will increase by this shadow price. Okay. Similarly, if you allow them to build one less unit, so 99 instead of 100, also the project save 50,000. Yeah, that's the meaning of shadow price. Yeah, sensitivity, basically. Yeah. So let's practice another problem. This is called path dilemma. Yeah, path dilemma problem. So you have only one variable here with this path space, and then we give you the shadow price of the water. Yeah, which is $50 per liter. Yeah. So, and then there is a new offer to you to have a new irrigation system that actually saves the water. Yeah. The new offer will provide you 1,000 extra liter, but the system costs 40,000. the question is, shall we take this offer or not? Yeah. So this one have only one variable. So you check. Yes, Lester. What do you think? Yes, take it.
Sir,
Yeah.
I think it's a good investment since
Yeah.
the total price for the water would be 50,000
Correct.
dollars and the system would only cost 40,000, so you have a profit of 10,000.
10,000. Yes. Very good. Yes. Yes. So knowing the shadow price, okay. So you will know the benefit, okay, because the cost is given, so you will know the net gain, right? So you build it. Yeah. So what do you think? The optimization, yeah, turn the vague debate into simple accounting. Yeah. So if you are confused, how can I get that shadow price? Okay. So I have the original problem of that pub dilemma. Yeah. So if you want, you can just check this one. Yeah. Originally, uh, actually one variable, okay, so that you can show it in there in a 2D. So I make it with the unit water supply. Okay, and then we have three constraints here. Let's try this one. I think this is interesting. No? Can you try this in the calculator? What is the objective function? Maximize the benefit. Yeah. So the water have no value to the profit, right? So in that case, you will put 0, the coefficient there. Okay. And then now you have three constraints. Okay. The supply limit. Yeah. You cannot supply more than 200,000 liter. So what is this? Water. So the Y must be less than 20,000. Yeah. This is the first constraint. And then the technology or the physics constraint. Each hectare require 2 liter of water. Yeah. So in this case, you just put this constraint there. Yeah. The last constraint is the land. Yeah. The land you have only enough up to 12,000 hectare. So there, X must be less than 12,000. Yeah. The last two, yeah, this is you don't need to type. Yeah, it's automatic. Yeah. So you practically only type the three constraint there. Yeah, which is the resources, the technology, and the land. Okay. So if you try that, you will get this value. Yeah? Exactly the shadow price that you want a while ago. So this one, you get the 4,000 is the allowable increase. Yeah? So if the offer is just for 1,000 liter, yeah, and then you are allowed up to 4,000. So if 1,000 is less than since 1,000 is less than 4,000, that means this shadow price is safe to use. Yeah, so you will accept the offer. Yeah. So what's the meaning of this range of feasibility? Yeah. So this range of feasibility here represent how much land can we buy before the price change. Yeah. So this calculator will tell you this also. Yeah. So look at the range and you will see the upper limit and it means you can buy 4 more, yeah, hectare safely. Yeah. So if you buy 5 hectare, then it is useless. Yeah. So this sensitivity analysis will also help you to make decision. Yeah. I hope this is useful for you. Okay. So, but be careful, yeah. When we said sensitivity analysis, yeah, this is only valid for a small change. Okay, so plus 1 unit or plus 10 unit. Yeah. So, but it's actually invalid for large number of units. Yeah, say 1,000 hectare land additional. So the shadow price may drop to zero. Yeah, because you will hit another traffic constraint instead. Yeah. So so don't extrapolate to infinity. Yeah. So be careful when you use shadow price. Okay. Check whether it will go beyond the constraint, the polygon boundary. Yeah. So linear model have a breakpoint. So you need to be honest with this limitation. Yeah. When we said sensitivity analysis, you are only talking about 1 unit change. Okay, not very big unit. Okay. Yes. Oh, really? Okay. So, okay, summary. Okay, so part 5, we will go next meeting. Yeah. So this is the summary. Yeah. So you have binding constraint, you have the slack, you also learn about shadow price. Yeah. So shadow price tell you exactly how much to pay for an upgrade. Okay. Okay. So up to here, thank you for reminding George. So, and thank you for today. And okay. Oh yes, it's always beyond. So see you next week. So your next week is your presentation, for your group project. Okay.
Thank you, sir.
Yeah. Thank
Bye,
you.
sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you po.
Thank
I
you,
hope
sir.
I hope clear enough the explanation.
Yes.
Yeah. Okay. Very useful. Very good. Okay. Thank you. Thank you.